Welcome back, ladies and gentlemen. We're going to be picking up where we left off. We had been talking about ions, and we'd been putting our ions together to make compounds, right? We went from simple things to more complicated things. Well, we learned about formulas and how to write these compounds in this chemical language that we are now using. Now, we have to take this a little bit further because while, we did learn about cations like sodium plus and anions like chlorine minus, and we learned how you can put them together in order to make a compound. And we saw that those compounds would look something kind of like this. And this, of course, right here is a chemical formula, much like a math formula. But much like a math formula, there are ways for me to write 4 and 4. Both of them tell you the same thing, but they're in a different way. In the same way, we can write NaCl in a different way, in a way that involves words. Now, in order to do this, we need to understand a few rules, but on the plus side, they're very simple rules. Step number 1. Well, let's start with a new color. Step number 1. Let's go with blue. What is the first element? The first element is always the one that is more left on the periodic table. We write it that way, right? That's why it's written NaCl, not ClNa. So the leftmost one in this case is sodium. So I'm going to write that. I'm going to write sodium. I'm going to need a little bit of room. Let's move the periodic table down for us. Heck, we're going to need this. So why don't we pull it off the wall and take a look. Sodium, of course, we know is Na because it is number 11. Right there. Now, the other one we need to find is, of course, chlorine, which is way over there on the far side. It is a halogen, right? Number 17. So I'm now going to write the second part of this, which is chlorine. Okay, there we go. We have chlorine written. But that's not the way that we do the words. See, chlorine is an atom, and these are ions. So we need to have a way to distinguish between the atoms and the ions. And why do we need to do that? Well, because otherwise it gets very complicated. Right? There's a very big difference between a chlorine atom that is still looking for one last electron and a chlorine ion that has that last electron. The first is incredibly reactive, and that makes it very dangerous. The second is actually quite inert, meaning doesn't react. And of course, it behaves totally differently in terms of its chemistry. So we don't leave it as sodium chlorine. We change the ending to be IDE. Sodium chloride. You've probably heard that before because that is the chemical formula and chemical name of table salt. Yeah, I know. Very fancy stuff. All right, let's try another example, shall we? I'm going to start us off with something a little bit more complicated looking. We're going to go with Mg3P2. Oh, look at that. We have so many numbers and things. And you'd think all those numbers are going to be super important. You think they're going to change the way that we behave and deal with stuff, but it doesn't. It doesn't in the slightest. Step number 1. What is the first element? The first element is this one here. If I check my periodic table, I see that that element is located on the left of the periodic table, and I see that it is Mg, is magnesium. All right, so the first word here is going to be magnesium. Then I have to check the second element, which is on the right side of the table, somewhere over here on the non-metal section. So I take a look and I can find it. There it is, number 15, right there, phosphorus. So I put phosphorus. Now, once again, we are not going to use phosphorus because this is not an atom, it is an ion. So we're going to take the ending and we're going to erase it. Now, roughly how much do we erase? Generally it's 3 letters, but it does depend. Try pronouncing it and see if it works in English. Phosphoride? Phosphoride? It's a little wordy. Let's try taking off even more. Phosphide? There we go. That's a little bit better. I wish I could say there's a pattern to these, but there really isn't. It's not just 3 letters. It's not just 4 letters. It's not just cut it off to the first consonant. It's just kind of a thing that you get used to. I know. But there it is, magnesium phosphide. Seem pretty straightforward? You have a few examples. Why don't you give them a try? And once you are ready, we can do the reverse. I'll give you a few moments. Pause the video, give it a shot. Okay, I can only delay so long. All right, let's try some others. We're going to be going backwards now. So rather than talk about a formula and we're going to make a word out of it, I'm going to give you a word and you're going to make the formula. So let's take a look here. Let's try one. Let's try aluminum oxide. Oxygen is one of those weird ones because it really cuts off a lot of the ending. So aluminum oxide. All right, well, black's coming out again. The aluminum we know is first. Aluminum is a metal, but it's not as far over on the left as you might expect. Right? The left of the metal's all over here, but aluminum is actually right there. Number 13. Underneath boron. Boron itself is a metalloid, a semi-metal, because of which side of the line it's on. But aluminum is a pure metal. We've got our aluminum, and then oxygen is the other one, so O. Now, we can't just leave it like this, because a formula, as we learned last time, is going to have some kind of a balance of sorts. Some kind of a balance. So we have to find some way in which to make sure that the aluminum and the oxygens are going to pair up nicely. Now, you may remember that last time we talked about doing that by showing a little diagram. So we're going to do it again just to make sure that we keep track of everything. So the aluminum has 3 valence electrons because it's in the boron family. The oxygen would have 6 valence electrons because it is in the oxygen family. So with this being in mind, I would take one of these and move it over, and one of those and move it over. And there we go. We now have a 2- anion, but our aluminum is not happy. Our aluminum still has 1 electron to donate, to give away. So it will, to another oxygen. So this extra electron here will come on down over here. Now the aluminum is happy. It is now a 3+. Oh, I've been doing that in blue. Let's keep consistent. It is now a 3+. But this other oxygen is not so happy. Well, that's unfortunate. What are we going to do? Well, we add another aluminum, right? The oxygen is going to keep shopping around until it gets everything that it needs. 1, 2, 3. Oh my, those of you who can think ahead are going to see a problem here, because while this aluminum here does give an oxygen an electron, making a nice 2-, he's happy, he's happy, he's happy. This aluminum isn't happy. So there has to be another oxygen. It's the only option. Now, on the plus side, we are basically done, right? Because if I look here, I can give one of these here and one of those down there. And then that is another 2-, and this becomes a 3+. Oh, once again, doing it in blue. Come on. And that's it. We now have all of the balance that we need. So if that's the case, what's my formula going to be? Well, count it. I have 2 aluminums and 3 oxygens. So when I make this chemical formula, I'm going to do Al2O3. And that would be the chemical formula for this. Now, why is it that the numbers aren't really listed in the formula at all? It's because all of these elements follow a very predictable pattern. Chemists don't like to do extra work they don't have to. And because all of this information is so obvious to a chemist, they don't bother explaining it. They don't define what hello is when they say it, because they figure you, the incredibly intelligent, handsome, and or beautiful viewer that you are, understand exactly what's going on. So aluminum oxide gives a knowledgeable chemist all the information they need about aluminum and oxygen and how those pair together. Because we know that aluminum is going to be 3+ and oxygen is going to be 2-. So we know these are going to work. Now, drawing all of this out, it's an awful lot of work. There are easier ways to do it. It's a bit of a shortcut. People always like shortcuts, especially when they find out about it after they've done a bunch of work. Let me show you. Aluminum and oxygen. Okay, we already know the answer, but there's a shortcut, as I said. The aluminum, as we already said, is going to be 3 plus because it's in the nitrogen family, and the nitrogen family is always behaving the same. Oxygen, on the other hand, is going to be 2 minus because it's in the oxygen family, and the oxygen family is always going to be the same. And now we do the shortcut. Well, wasn't that nice and quick and easy? All right, there's actually a bit of a problem with this. There's one particular situation where this won't work well. That situation would be for something like, say, this. Oxygen, as we just said, is 2 minus. Magnesium, we'd have to look up. What family is magnesium in? We pull out our trusty periodic table, we take a good look, and we see magnesium is right here under beryllium. That means it's going to be 2 plus. If I make that 2 plus, and I pull it down on both sides, what's going to happen? Well, things get a little messy. Because I'm going to write Mg2O2. That kind of implies that I need 2 magnesiums and 2 oxygens to combine together in order to make this thing, but I don't. I only need 1 of each. So we'd actually just put MgO. Basically, for those with a little bit of math knowledge, what we're dealing with here is a lowest common multiple. We are going to divide by the lowest common multiple. In this case, it's 2, and we're going to get rid of the 2's and put it like so. In the case of aluminum oxide, that's not an option, right? It's locked in place. It's just Al2O3 because I can't divide either of them by the same number, right? I can't divide by 2, I can't divide by 3. So we're kind of stuck. There's another way to look at this. This is a little bit more mathematical. So like this way with the drawings will work pretty much every time, but it's a lot of work. This way here called the crisscross method is a very simple shortcut, but it's kind of lacking because you need to remember to divide at the end. The last method that I probably recommend the most is going to be something very simple. We're going to continue with aluminum just because we already know the answer. So aluminum and oxygen. We know that aluminum is 3 plus, and we know that oxygen is 2 minus. So how many aluminums and how many oxygens do I need for these two to be balanced? What number can I multiply both of them by in order to get the same thing? Well, I could multiply the aluminum here by 2, and that would give me a total of 6 positives. I could multiply the oxygen by 3, which would give me a total of 6 negatives. If the two of them are equal, we've done it right. So that means this is going to be Al2O3. Everything in chemistry wants to be balanced. Everything in chemistry wants to be the same. In the case of the actual individual atoms, they fill up their valence shells from the ions fill up their valence shells from the atoms that originally had something. And now that they've filled up their valence shells, what we can see is that they start to balance each other in order to ensure that they remain neutral, which is why they have ionic bonds, in order to make all of this come together. Anyway, those are 3 different ways in which to figure out how to go from names to formulas. With those in mind, I would like you guys to do a bit of practice. It's actually probably an awful lot of practice. And once you've worked through it all, we will be able to continue with a little bit more complicated. We're going to be pulling out that whole middle section of the periodic table. But practice first, and I will see you guys next time.